In this podcast, we're going to show how the ideal gas law can be used when one or more of the four variables are changed from one situation to another. For example, here is our ideal gas law, PV equals nRT. If we go ahead and solve algebraically for R, we get PV over NT equals R. We have two different situations. We have before the change and we have after the change. And since they both equal R, we can put them both equal to each other. So you end up getting this for the combined gas law. One thing to keep in mind in this combined gas law is that if two variables are next to each other, they're indirectly proportional. A good example is if I take a balloon and I decrease its volume, the pressure will go up. So you see how as one goes down, the other goes up. Conversely, if they are on top of each other, generally they are directly proportional. For example, if I increase the temperature, the volume will go up. Now this is assuming that all the other variables, or two of the other variables, are held constant. For example, if the volume and temperature are held constant and I increase the number of moles, then my pressure will go up. Here's an example that shows the combined gas law. A diver blows a 75.0 milliliter air bubble 10 meters underwater. As it rises to the surface, the pressure goes from 2.25 atmospheres to 1.03 atmospheres. Assuming the same number of moles are present in the bubble and the temperature remains the same, what will be the new volume of the bubble at the surface? So essentially what we're doing is we're blowing a bubble under high pressure conditions and the bubble is rising, going to a lower pressure situation. So here's our combined gas law. And what we'll notice is that the number of moles stays the same and the temperature remains the same. So essentially those are going to cancel each other out. So we don't even need those in the equation. So I'm going to go ahead and get rid of them right now. So we're left with just P1V1 equals P2V2. So let's plug in our values. At 2.25 atmospheres of pressure, the bubble was 75.0 milliliters. Well, we want to know what the volume would be at 1.03 atmospheres once the bubble reaches the surface. Solving algebraically, we get 164 milliliters. So let's notice, as the pressure went down, the volume went up. They're next to each other. It's indirectly proportional. One goes up, the other one goes down. Notice that the volume is in milliliters because the volume on the other side of the equation was also milliliters. Keep that in mind when you solve these equations, that units have to be the same on both sides. Here's another example. A helium balloon in a closed car has a volume of 2.32 liters at 40 degrees Celsius. If the car is parked on a hot day and the temperature inside the car rises to 75 degrees Celsius, what will be its new volume? So here's our combined gas law again. We're going to assume that the moles of helium inside the balloon are going to remain the same. We're also going to assume that the pressure is going to stay the same as well, because the balloon can expand. So that leaves us with just V1 over T1 equals V2 over T2. So let's go ahead and plug in our values. Before the change, we had 2.32 liters inside the balloon. Now let's look at the temperature here. Notice I put it in Kelvin. 40 degrees Celsius is 313 Kelvin. So before the change, it had 2.32 liters of volume and 313 Kelvin. After the change, the temperature went up to 75 degrees Celsius, which I also put in Kelvin at 348 Kelvin. When I solve for volume 2 in this case, I get 2.58 liters. Notice the volume is in liters because the volume on the other side of the equation is in liters. And let's look. When the temperature went up, the volume went up. A direct proportion because they're on top of each other in the equation.